All right, so today we're going to calculate the E standard cell, E actual, and Gibbs free energy for the following cell reactions. We have a magnesium solid plus tin 2 charge yields magnesium 2 plus charge aqueous, tin solid. Tin solid where the magnesium concentration of a 2 charge is 0.045 molarity and tin is 2 plus charge of 0.065 molarity. And then we have our second equation, which is a 3 zinc solid plus 2 chromium with the 3 plus charge aqueous yields a 3 zinc 2 plus aqueous plus 2 chromium solid, where the concentration of chromium with 2 plus charge equals 0.070 molarity and zinc with 2 plus charge equals 0.0075 molarity. Now the first thing we're going to have to do is we're really going to have to understand what we're looking for. So it asks us to calculate for all of the above here. So here, just made a quick layout for you guys. It asks us for E standard cell, our actual E, and then also asks us for free energy, Gibbs free energy. So we're going to start off here with our E standard cell EMF. So you got your E standard cell EMF equals your E cathode minus your E anode. Now your E standard cell EMF is here, which you can tell the difference because of the little degree that it has here in the cell as opposed to the actual one. Your E standard cell EMF is your electromotive force. Now, mind you, the electromotive force is a measure of voltage, not force. So just keep that in mind, okay? Your cathode is a reduction, is gaining electrons. So in your cathode, just remember constant is C, and then R is also a constant. So you can remember reduction and the gaining of electrons. Now your E anode is your negative, so your oxidation is losing electrons. And you can remember that also because your vowels. A is a vowel, O is a vowel, anode, oxidation. All right. And also keep in mind that the E cathode minus the E anode are the standard half cells respectively. So they're just half cells. Okay. Also we have here is the E actual EMF, which is also the electromotive force. Keep that in mind. EMF, electromotive force, it's good to know, equals your standard cell EMF minus 0.0592 voltage all over N, which is your number of moles, times log Q. And your log Q is just the reaction quotient. Okay? These are what we'll be using. And then lastly, delta G, or Gibbs free energy. This equation equals, or the formula equals, negative N Fe cell, which delta G is Gibbs free energy. Negative N is the number of moles of electrons, times Faraday's constant, which is 96,500 joules per voltage times moles, and the E cell, which is the E cell potential. Okay? So after reviewing that quickly, let's sorry, get my marker. So the first thing we want to do is we're going to look for E standard. Okay, and remind you that our E standard involves your cathode and your anode. So the first thing we want to do is create a half reaction for each of those. So if we know we have magnesium plus zinc with 2 charge plus yield to magnesium 2 plus aqueous plus zinc solid, what we're going to do is we're going to break them up and we're going to create our half reaction. So we have a magnesium solid. Okay, it's going to yield a magnesium 2 plus charge aqueous. All right, and you see that we just took it from here to here, just yield it, and we're going to do the same thing. Okay, we're going to do the same thing with our zinc. So it's going to be our zinc 2 plus charge is going to yield going to yield our zinc solid. All right, and this is going to be aqueous. Make sure we have it there. Okay, so from here, we're going to find our cathode and our anode, and we have to see pretty much which one is reducing or which one is oxidizing. Now, here, you can tell that your magnesium has your 2+ charge, and it's oxidizing your anode. So it may look a little better if we just add your molarity here, which is going to be a 1.0 molarity. Okay, and then it's going to add 2 electrons here. Sorry, I forgot the 2. So pretty much what's going on here is you have here, you're losing 2 electrons, and that's why you're writing your equation like this. Okay, and in that case, if you know you're losing 2 electrons, like we said earlier, oxidation is losing. Okay, so you know this one's going to be your anode, so we'll label that anode because it is losing electrons. And then we have our zinc. So if one's losing an anode, this one can also be losing, but in this instance it's not. So here what we would do is we would actually write this a little different here. So it'd be SN2 plus aqueous, and then you're gonna add your electrons here. So we would know as standard this would be 1 molarity plus 2 electrons yields tin solid. And the reason why we're doing that is because here you're actually reducing, and it's your reduction, so it's going to be your cathode. And as you can see, what you're doing is you're giving off 2 electrons. So with your 2 electrons, you're actually gaining electrons, as you can see here. So this tin is giving off your electrons, yielding all the way to here. So you're actually gaining your electrons. So we know this is our cathode. So now we have our anode and our cathode. Now the reason why we're doing that is because our E standard cell, the equation in there wants us to find our cathode and anode in order for it to work. So now we have our E standard cell equals our tin over tin 2 charge minus our magnesium 2+ charge over magnesium. Our Ecell, our equation is cathode minus anode. In order to find the numbers that I'm going to put up right now, you're going to have to use the half reaction standard reduction potential chart. All right, so to find the voltage, so we know that zinc is going to yield, according to that chart, it's going to yield a -14 voltage. So let me write here. It's going to be 0.14 voltage. Okay, and here we know that's our cathode. Okay, because you can see here, this is our cathode here, this is our cathode down here, and it's going to minus our anode, which we found here, anode for magnesium, and that's why we have it here. So it's going to minus our anode. So it's going to minus our anode, which is going to equal a -2.37 voltage. And then when you do the calculations for this, it's going to come out to 2.3 voltage. And that's going to be our E standard cell. So E standard cell equals 2.23 volts. Now the next question is going to ask you to find your actual cell. Okay, and in order to find your actual cell, you need your standard cell. That's why you look at your standard cell first. Okay, so now we have this equation here, where E actual equals your E standard cell minus 0.0592 volts over N, which is the number of moles log, and our quotient reaction, which is our Mg2 plus over Sn2 plus. Now you know this by your anodes and cathodes. Your anodes will be on top and your cathodes will be on the bottom. Okay, so if we plug this in, we have our E cell. Remember, our E cell is 2.23 volts. So our E is going to equal 2.23 volts minus our same number here, which is 0.0592 volts over the number of moles. Now we could find the number of moles by the charges here. And here we have an equal charge, so we don't have to multiply or anything. We just know our charge is going to be the 2 plus. So we know we're going to have 2 moles here. So we put a 2 here. And then it's going to be times log, and then the quotient reaction. Now in the quotient reaction, as you can see here, there's brackets. Brackets represents the concentration or molarity. So with this, it's already provided to us here. So we got 0.045 and 0.065 molarity. So we're just going to plug that in here. 0.045 over, this would be molarity, over 0.065 molarity. Okay, so if we calculate this out, you should put everything in the calculator. It should be nice and simple. You should come out with 2.23 volts, which you can tell there's really no reaction from that, but that's fine. Okay, now the third thing they're asking us is to find Gibbs free energy. Oops, excuse me. Sorry about that. Alright, so just do that here. Be a lot easier. Okay, so now they're asking us to find Gibbs free energy, okay? And this is rather simple. It comes out pretty nicely because we already know the number of moles that we have. Okay, it's going to be 2, as we've seen earlier, because we looked at the charges up top here. We know that, okay, we have a 2 charge. That's going to be the number of our moles. And we just start plugging away, okay? Because we found our E cell voltage already, our potential. So just make sure you keep Faraday's constant in mind, 96,500. So we're just going to start off by plugging everything in. So we're going to just put our free energy, or Gibbs free energy, delta G, and then it's going to equal the number of moles, okay? And we know our number of moles is 2 times Faraday's constant, which is 96,500 joules per volt times moles. So 96,500 joules per volt times moles. And then lastly, our E cell potential, and we found our E cell potential earlier. We found it earlier here, okay, which is 2.23 volts. Just plug that in here. 2.23 volts. And it's simple as just multiplying everything together. And so you're going to have -2 times 96,500 joules per volt times moles over 2.23 voltage. All right, so these are moles. You just want to make sure you keep those in mind. 2 moles. All right, and then our answer, once you calculate every single thing out, you should equal -431 kilojoules. Okay, make sure you always want to convert it to kilojoules when it goes to Gibbs free energy. All right, so my apologies. Here you're going to get your joules, and when you get your joules, you're going to want to multiply by kilojoules. So your kilojoules is going to be 1 kilojoule over, and then it's going to be 1,000 joules here. So you're going to multiply from your voltage times your joules, and that's how it's going to get you to kilojoules. My apologies. Okay, and that's going to be that. Now we'll just pick it up at a little faster pace this time, and we're going to do the second equation here. I'll actually start a new video for this.